Right. Hi, Year 10. Today I'm doing a lesson as part of the C5 module, and we're going to be talking through how we explain energy changes in chemical reactions. Okay. So far, you have been taught this week about exothermic and endothermic reactions and what those terms mean. You've also looked at planning a required practical for this. Carrying out the required practical, obviously, we've not been able to do. So now we're going to be looking at energy and how that changes and what's going on and what we call these reaction profiles. Okay? So hang on to your seats and we're going to get through this with plenty of time so that you can spend some time looking at it and having a look at some exam questions as well in order to submit those to your teacher. Okie dokie. So where are we going with this and why are we learning about it? What we've got is, there we go, a bit of delay there on my computer, which is always fun. Here, why are we learning about this? Well, you've already learned about the use of heat packs for back pain, cool packs for sports injuries, physiotherapists, first aiders, all sort of interested in this, as well as all those camping enthusiasts, okay, with the self-heating cans. We can get tins of beans that, there'll be a chemical reaction side that will heat the beans up and, you'll be able to eat your beans in comfort without needing a campfire. As well there are plenty of other examples of this. So first, quick recap. We've got exothermic and endothermic reactions. What we can see here is that you've got various statements on the slide. If you pause the video now, then you'll be able to have a go and think, right, which of these do I think is exothermic and which do I think is endothermic? And just write down or jot down, make a note of the ones you think are which, and then we'll go through them. Okay, hopefully you've done that. So let's go through. I've marked on there the exothermic ones with a big red X, and you'll see why a bit later. The red X is linking to exothermic, that word, and trying to help you remember that. So exothermic reactions are ones that feel hot, ones that give out energy, ones where we see a temperature increase, ones where we often see combustion, something burning, okay? One where the heat is given to the surroundings. An example is hand warmers. All of the other ones on here would be an example of what's happening with an endothermic reaction, okay? So the opposite type of chemical reaction. Okay, so done a quick recap on that. Let's now have a look at a bit of physics, but it actually applies to all science, including biology, when we start talking about energy. Okay, the law of conservation of energy is a really, really important aspect to get in your head, okay? Energy cannot be created or destroyed. Yeah, it can only be transferred from one form to another. So we've got here this idea that every single molecule, a molecule of oxygen, a molecule of water, a molecule of methane, a molecule of glucose, they all contain chemical energy stored within the bonds, making up that molecule. After any chemical reaction, like it says there, the amount of energy, the total amount of energy in the universe will always remain the same. Okay, you can't heat up your tin of beans and that's going to use up some of the energy in the universe. It's not. It's merely going to take some energy from somewhere and transfer it to somewhere else. Yeah. So when we come to look at this, if you see, and we're going to be looking at some graphs, that we start with a certain amount of energy and we end with a lower amount of energy, you can't do that. You can't just, that energy can't disappear. So it's got to go somewhere. Okay, so it has to have gone. So if you have more energy and then you end up with less energy in your chemicals, then that energy difference has to go out to the surroundings. Okay, likewise, if you start with a low amount of energy in your molecules and then you end up with a new compound that's got more energy, well, you can't just invent energy. That energy that goes in to make up the difference has to come from somewhere. And so it takes it from the surroundings. And so what we're going to look at is how our endothermic and exothermic reaction profiles, these graphs, look like. And if you can get them in your head, you really, really will be well set for some exam questions. Okay, so the chemistry, let's get through this. We're looking at this idea of a molecule of hydrogen being split into two atoms. Okay, we are breaking these bonds. Okay, and so generally, when you're breaking bonds, okay, you can think that you're going to need to put energy in order to break those bonds. Okay, and so if you're putting energy in, then the direction on your graph is going to be going up. You're going to be going up. Okay, because your energy levels are going up. You're putting energy in. All right. When we look at are we moving on or not? There we go. When we look at making bonds, so here the opposite process, okay? Here, where we're taking two separate atoms and sticking them together to make a molecule, to create a bond that wasn't there, then this often involves transfer out of energy, okay? And this is shown by a fall in the level of energy. So generally, or not generally, always your graph is going to follow the pattern of energy is going in, so to break bonds, so we're going to go up, and then we're going to lose some energy as those bonds are formed. And depending on how far you go with regards to how far up you go, and then how much energy is given out and how far down you come, that determines the shape of your graph and whether it's an exothermic or an endothermic reaction. Okie dokie. So we've got here an example where we're splitting apart our iron oxide. We're breaking this bond, so we're putting some energy in. Then we are reforming a magnesium oxide. So we are creating a bond, okay? And so that's going to then transfer some energy out. And depending on which one is larger than which will determine whether or not we end up with an exothermic or an endothermic reaction. Okie dokie. So here is an example of what a reaction profile looks like. Okay, and what you'll see is, or what you'll notice is that when we look at all of these, they all have basically the same shape. Okay, all that's different is where you start on this axis here with your energy. Yeah, where you start with the amount of energy in your reactants and where you end up with the amount of energy left in your products. Okay. So what we see is as the reaction progresses, the reactants will turn into the products and we will have our graph. Right. In exothermic reactions, the energy of the reactants is greater than the energy of the product. So this line is higher, more energy, than this line, which is lower. Okay. What we've got here is our reactants need to be split apart. So we have to put in some energy to do that. We call this the activation energy. And then once we've split them apart and they can rearrange themselves, we then get bonds forming and we get energy given out. And in this case, we get given a lot of energy being given out. Okay. And then we create our products. And that difference from where we start with our reactants, the amount of energy, to where we end, the amount of energy in our products, we call that our overall energy change. And when you look at your spec, the things they want you to know are, can you identify the energy level of the reactants and the products? Can you identify or draw on a graph or label the activation energy? And can you label the overall energy change? Those are the three things, the reactants and products, activation energy, overall energy change, that you must focus on. Okay, so then, if we can move on, here we go. We now have a look at an endothermic reaction. And you'll notice it looks very similar, okay, and I'll grant you that. But what you'll notice is that now our reactants have a lower amount of energy than our products. We still have to put energy in to go up to break some bonds, but when we reform the bonds, okay, we don't get as much energy given out as we have to put in to get to split them apart. So we need to add energy, okay, into our reaction, and that energy comes from the surroundings, okay. So when we look at the two next to each other, if we have a look at, let me try and go back. Sorry about the delay on this. Here, what we notice is our exothermic, these are the ones that give out heat, they get warmer. We put in some energy, and then we get a load of energy given out from the making of the bonds. That's the amount we need in our products. But the difference, the overall energy change, is the difference between the two. And so that is given out as heat, okay? When we look at our endothermic, here we start with this amount of energy, we go all the way up, we put in a load of energy to break all those bonds, and then when we get back, we get given back only this much energy. So actually, we've had to give in this much energy into the reaction, and that energy has come from the surroundings. So it's taken from the surroundings. So the surroundings get colder because they have to give the energy to this reaction in order for it to happen. Okay, so we've got a summary slide here showing you what you need to be able to label: the reactants, the products, the total energy change, and the activation energy. Linking that to getting hotter, getting colder. We'll have a look at energy levels, this bottom row here, in another lesson, and that's more for the higher tier. But why don't you now have a go at testing yourself? So pause the video now, read that, have a go, write down what you think, whether exo, endo, etc., and then restart the video to check. Okay, let's find out what they are. So we've got our exothermic, where the temperature is increasing, endothermic, where it's decreasing, exothermic, where it's increasing as well. So hopefully you got that. The next bit here, if you don't, I'm not expecting you to print this off, but you can sketch your graph here, okay? And this little line coming across is sort of saying the zero line. So if you imagine this is energy in, if we come below that, it's energy out, negative energy. So here, on this first one, sketch what you think is going to happen for each of these. We said here we've got an energy change of plus 208, so that means we've got to add 208 kilojoules per mole. So this is an endothermic. And here we've got 76 kilojoules per mole of energy being given out, okay, left over. So this is an exothermic. And let's pause the video, sketch your endothermic and exothermic, and then have a look to see if it's similar to mine, and label activation energy and your overall energy change. That's important. Okay, so hopefully, sorry about my squiggles, but hopefully you were able to here show an endothermic where you're increasing, giving more energy than you get back. Okay, so you've got to add, you've got to put that energy in, yeah? Whereas here, we're going from a higher energy level and then we're giving out energy. Okay, so we're coming down, and this is going to be an exothermic where we've got a loss, a decrease. We're going from there to there, which is why it's considered a negative. Whereas here, we're starting at this point and we're going up to this point. So we've got to put in that amount of energy. Okay, have a look at the rest of the work questions on Google Classroom. Hand those in to your teacher, and I hope that you've at least gained some understanding or some partial understanding of these reaction profiles and how you have to be able to label the different parts. Okay, this was what we were hoping to cover today. The different reaction profiles, identifying which one's exothermic, which one's endothermic, and that the activation energy is the energy needed for a reaction to occur, that the energy you have to put in, to break those bonds initially before you then get the formation of the new bonds. All right. Let's end. Where are my controls? They gone. There they are. Brilliant.